Hello, everybody. Thanks. My name is Philip Cardiff. I'm a professor here in the School of Mechanical Materials Engineering. Welcome to Computational Continuum Mechanics 2. Most of you will have done Computational Continuum Mechanics 1 last year, if you remember, with Alois. So this course takes a different perspective. It's an add-on, but it takes a different perspective to Computational Continuum Mechanics. So where that course is very much theoretical, and let's say a bottom-up approach. So start from basic mathematics definitions, build up different definitions of physics, and then at the end you can see in the distance what a finite element software might look like. Whereas this module starts, let's say, with the software and how to use it, and takes a top-down approach. So trying to connect that back to this. So hopefully there's no gap between CCM 1 and 2, but that's the kind of the idea or the philosophy. So in the lecture today, I'll just give you an introduction to the module, tell you a little bit what it's about, what we're going to do, and how it's structured, how to pass it. And then if you have any questions as well, I'm happy to answer them. So what is this module about? And by the way, I'll try, if I remember, to record the lectures via Zoom, so I'll try to upload them as well afterwards. I have some recordings from previous years I've uploaded, but I'll try to remember to record these as we go. So how would you answer any of the following questions? So I'm going to give you graphical questions. So for example, if you were working for a wind turbine manufacturer, sorry, let me see if I can get rid of this thing. Okay, cool. And you were deciding you had a certain wind farm to commission, and you wanted to determine the best location, or the optimal location to place the wind turbines. So you could put them in a grid, that might work fine, but there's various things you might want to consider. You might want to maximize the average total power output from the wind farm, but also you want to minimize maybe the fatigue on the blades, because that might be the bottleneck for them being maintained or replaced. So if there was a little hill and then you get a recirculation zone of air, then that might cause the blade to fatigue a lot. You put a wind turbine behind that. So how can you test that? You could build a wind model in a wind tunnel, or you could use computational fluid dynamics, so simulation techniques that we're going to talk about to try to answer that question. So for example, Vestas is one such company, and they'll use techniques like CFD, or computational fluid dynamics, to determine the best place to locate individual turbines. But also you could use the optimize individual turbines or individual profiles of the blades. Sticking with the computational fluid dynamics, so obviously Cybertruck that has been optimized, the aerodynamics has been designed in a particular way to reduce the drag, and has a particularly low drag, but also more high end. So Formula One, this is an old one. The front wing has looked different now, but they're optimized very, very tightly based on computational fluid dynamics. And the teams have limitations on their computing hours. So when they make a change, they have to show it's within the maximum computing hours that are allowed to use per season as well. So these are well-established technologies. So similar to computational fluid dynamics, there's computational solid dynamics, and it's the similar idea, but you're looking at when is something going to break, or how much is it going to deflect or move, and will that be okay for its intended application. So it might be the wing of a plane or fuselage or something like that. So often a synonym for computational solid mechanics or dynamics is FEA. People call it FEA, but that's a poor name. FEA is one particular method for computational solid. So finite element analysis is often used, but you can use finite difference, finite volume, spectrum methods. There's lots of methods, but FEA normally means stress analysis. But we're going to talk a little bit about this in this course as well. Closer to home in Ireland, we have a lot of medical device companies. Many of you will have done internships at medical device companies. So, for example, for stents, many of which are made in Ireland, the manufacturers will perform stress analysis on them to check if they will behave how they want them to behave. So typically, once again, fatigue is important. So they might look at the min and max strains, min and max stresses on their cycles in if they're in vivo. This is a project I'm involved in. So Dylan recently had a paper published on this. So Dylan's only a teaching assistant for one of the labs. He's a PhD student there. So Dylan worked with Boston Scientific, and they make these heart valve replacements. So this is a aortic heart valve. And so these are made in Galway. And so these are the transcatheter ones. So they squash them, put them into your leg, go into an artery in your leg, go the whole way up to your aorta, and then they kind of pull a sheet away and pops into place. Okay, that sounds easy, but it's obviously highly complicated. But from an engineering perspective, there's a lot of design challenges. So obviously you don't want the blood going, you want it to block the blood, but you also don't want blood going around it. And you don't want this device to move after you put it in place. And also, typically these have to be certified to 1 billion cycles. So hundreds of millions, if not a billion. So they have to be on it. So that could be a 3 to 6 month test. So simulation that gives you particular unique insight into how to design devices like this. Second in this cardio space, and highlighting some other research I'm involved in. I'm actually looking for PhD students. So if any of you want to do a PhD from next year, I know it's far away. You've only started final year, so you're not thinking about that. But I'm just putting the seed there that there's lots of PhD projects here, but also around Ireland or abroad. So in particular, we're going to be working on making models for the heart, but also for pig hearts as well, because there's this area called xenotransplantation. So maybe in 20 years, if you have a problem with your heart, you get a pig heart. Something like that. Okay, I started with some questions of how would you answer these questions. So you might not even remember that question anymore, but it's good to show the diversity of the different applications. So let me just go through a few more before I tell you how you can answer. So metal forming companies. So this is a company that designs rolling devices. So like sets of rolls to make certain shaped devices. So if they want to set up their rolling machines, and there might be 12 rolling machines to get a particular shape, it could take 12 weeks to do an experimental cycle. So they will design the rolls, have them manufactured, ground, run the test, analyze the results, and then decide if it was able to create the geometry. So obviously, if you could do that somewhere virtually or do some calculations, that might help. 3D printing or additive manufacturing, many of you will have experience with this or get into this area. IFORM is a national advanced manufacturing research center, which is hosted in our school here in UCD. So here's an example of a laser beam powder bed fusion type model. So a laser beam is melting the particles, the metal particles, and there's lots you can do with models like these. Okay, 2 or 3 more examples I have. So this is very much not limited to mechanical engineering. So these types of analysis are of interest to many different people. So there will be colleagues in, say, chemical engineering as well. They're designing mixers and they'll use tools like this. Also civil engineering. So when you build a building, you don't want people to be blown over as soon as they step outside of it. So any of these large buildings in the Dublin city centre now will have computational fluid analysis performed on them. Check. They call it pedestrian comfort analysis. So when the architect says, "Oh, here's a nice little place to sit down and have a cup of coffee," if the wind is too high at that location, nobody will have coffee there. They won't sit down because it's too windy. So there's something called a Lawson criteria where people can do the calculations that if the average wind speed is below a certain threshold, and then people will be happy to sit there. Otherwise, they won't be comfortable. So this is a famous building in Manhattan called the Flatiron Building. It's over 100 years old. So when they designed that, they didn't use CP, but it's designed like a wing. So the movement accelerated around it. So it's well known people get blown over. And similar for bridges, analysis like this will be performed on bridges, which get the safety for the bridge, but also for the traffic. I think this is the last example I have. And then also forensic engineering. So when something goes wrong, they'll often get people to perform analysis to try to understand why. So this is in Donegal Airport in the early 2000s, when the new, a second new terminal collapsed in the airport. Unfortunately, people passed away. So as part of their design, they reduced stress analysis tools, and they just made some poor assumptions and used them incorrectly. So then, in subsequent analysis, they determined what assumptions were incorrect. So it was around 49. Okay. So what are the relative merits of using simulations? Disadvantages, limitations. Just to get some interaction, I'll use poll ED. So I'll just get you the, I won't get a whole load of input from you during the module, but I'll just once anyway. So if you want to go to polled.com and the module code is MEEN40150, or you can use the QR code. It's not turned on yet. You'll be able to log in, but when people stop scanning the QR code, then I'll turn it on. So if you want, you don't have to, but if you want, you can just post an advantage, disadvantage. What are good things, what are bad things do you think of simulations? Maybe you came across simulations in your internships or previous experience. Yeah, give me a second, I'll just turn it on. Okay. So it should be active now, I think. Okay, should be active. I think you should be able to see it in post now. So I'll share my screen again. Okay, so as you post, and they'll come up here just so you can see what other people are posting. I have moderation turned on as well, so enjoy yourselves. So I'll just do this for a minute or so you can see what other people are posting. So most of these are all the advantages. So maybe if you post an advantage, think about a disadvantage. Is there any, if it's simulation so amazing, why is everybody not using it all the time everywhere? Or maybe we should. Okay, the last 30 seconds if you want to post them. And then I'll just have a quick look through them and comment. Okay, I'm going to do a quick look. Can I scroll here again? Okay, cool. Okay, so I think mostly people started on advantages at the start. So performance allows rapid evaluations, and cheaper, faster, cost benefits, cheaper, faster. So a lot of the reasons you might use it is it might just be faster than an alternative analysis technique, whether that's experimental or something else. And might be cheaper as well. Faster and cheaper are closely linked. Safety is an interesting one. Yep, definitely. If you look at the medical device space, say the accreditation bodies in Europe and America are definitely starting to push medical device designers into the area of they expect you to do stress analysis. Whereas in some industries that might already be the standard. So for example, like the nuclear industry or something like that. Minimizing cost, efficiency. Yeah, so this is a con. Troubleshooting could be a con or a pro. So yeah, I guess in terms of a big disadvantage, correlating between real life and simulations. So maybe we'll use the word validation for that. How do you validate the model? So after you run the model and it says, oh, no, this wind turbine's fine. How do you believe that? Because there's a big risk if that's wrong, that could destroy your company, for example. And so that is obviously very important. No need to manufacture to test. That's a potential advantage if you don't have to make all these prototypes. Foresight, predictions, efficiency, very good. Speed, find flaws, time savings, validation, computational. Oh yeah, difficult to set up. So they're not simple softwares. Currently, they're not easy softwares to use. So hopefully, through this course, you'll at least be able to use them and go on to use them later if you want to in your careers or whatever you do with them. But you'll see they're not trivial softwares to use. You kind of need to know what you're doing. Even if you think you know what you're doing, also you can also get very wrong results. So they're not easy to set up. So expertise is a challenge. And computationally expensive as well. So for example, that heart valve simulation took maybe 12 hours on 300 CPU cores. So that was on a supercomputer where we were using 300 cores. So say my laptop, this is my older laptop, it's maybe an i7, so it has 4 cores, I think. So there's 4 units inside the CPU that do calculations. So if I click on something, there's these 4 little calculation engines. So if you have a large supercomputer, you can have multiple CPUs and multiple nodes. So that was taking 300 cores, 12 hours to run. So that's not something you're going to do on your laptop home, obviously. So computational expense, people will now, you can run things in the cloud, but then you have to pay Amazon or Google Cloud as well. So then you have to weigh up the cost of that or decide to invest in a 100 grand computer and weigh up the advantages of that. Accuracy, energy, difficulty to account for all real world parameters. Yeah, a lot of problems are just really complicated. And as we'll go to talk about in this module, when you set up a model by definition is an approximation or an idealization of reality. So it has limiting assumptions. You never capture all of reality. So some things in real world are just so complex that whatever you're interested in, it might not be easy or possible to get some insight with these types of models. Expensive software, yeah, many of these softwares, we're going to use 3 softwares. I'll tell you about them later, but 2 are commercial. 1 is open source. 1 is a free software anyone can download. The other 2, you require licenses, and we get them cheaper in universities, but if you were to pay in a company, they might be 40,000 euro per year for 1 person to use them. So not cheap. Okay, we go back. Any other comments or questions, please, Mike? So why would an engineering company or any company use numerical modeling instead of performing experiments? So primarily, experiments are normally expensive, and simulations can often provide a cheaper solution. So I'm not going to make a categorical statement. Sometimes models can be very expensive as well. But often experiments are more expensive. But that's not always the case. Sometimes it's easier to something small, you can just make it, test it. That's quicker and cheaper than doing the model. One general statement you can normally make is simulations provide a unique insight into the physics, which is not always possible with experiments. So if we take the heart valve example, then we can look at the stress and strain at every location in that heart valve, including the leaflets and the night tunnel frame. Whereas in an experiment, and even with the most advanced experimental optical or measurement techniques, you can't see inside the things or see everywhere at the same time. So there's insight that you get with models that's just not possible. This one's a bit less tangible though. And then sometimes people say simulations are more accurate than experiments. So as a counter example, that's not true. So if we design a wind turbine, you build it and it breaks, and you make a model and the model says it doesn't break. So which one is real? Which one's true? So obviously whatever happened in reality is what happened. And I will put a caveat on this. So models can more accurately reflect reality in small scale experiments. So if I take the wind turbine example, you may make a scale model of a wind turbine and test that in a wind. So you have a scale model of a real wind turbine. That scale model will not behave exactly the same as a full scale wind turbine. So you have to apply some scaling to that analysis to scale up your results. So that scaling is not perfect. So in those scenarios, when you're doing scaled experimental models, and some other cases when experiments are approximations of how it's going to the actual device of interest, then models could actually be more accurate, but that depends. Okay, so in this model, you're going to learn about how to perform numerical simulations of solid and fluid systems. If you haven't found the module, you should just search on Google for, where is it? Here. Just for the module code on Google, and it should come up. So you'll find most things you need to know about the module here. But in short, you're going to learn 3 softwares. ANSYS Fluent. So ANSYS is a software suite. We're going to use a software within ANSYS called Fluent. This is a fluid analysis software. It's a commercial software. We're going to use Abacus is the first one. Abacus is a finite element commercial software. Both of these have been around for 30 plus years, and probably 40 plus years. And then we're going to use an open source software called OpenFOAM. And that will be the last one we use. So that's a free software, mostly for computational fluid analysis. So at the end of this module, you should hopefully be able to set up some heat transfer, solid mechanics, and fluid dynamics type analysis in these software. That's the general idea. But the course is aimed at an educated user. It's top down, like how to use the softwares, but use them in an intelligent manner, not to produce terrible results or results that might hurt someone or make you lose your job. So we're going to connect some of the important things, choices in these softwares to the underlying theory. So we're going to talk about errors mostly. So there's different types of errors that might make your analysis invalid, and how can you estimate them and how can you control them. So we're going to talk about numerical errors, modeling errors, and within numerical errors, discretization error, and other errors. And then we're going to talk as well about verification and validation and the difference. And then near the end, OpenFOAM is predominantly run through a Linux terminal. So you're going to learn a little bit about Linux. It's not that difficult. And finally, we're going to introduce you how to use a supercomputer. So in UCD, we have a supercomputer called Sonic. And we also, as all of you may not know, but you also have access to a larger computer via UCD, which is one of the larger computers in Europe called Galaxina. But we're going to use Sonic. And the last lab is you have to run a job on 40 cores on Sonic. Okay. How do I pass the module? So this is, I guess, is the most critical thing. Oh, okay, let's take that again. I'm going to stop sharing my screen every time. For some reason, it's Zoom. Okay, let me share my screen again. Okay, how do I pass this module? So it's on the module descriptor. So a lot of times I'm just going to direct you to module descriptor rather than copying and pasting, because I've made a mistake in the past where there's an inconsistency between the assessment in my lecture slides and on the module descriptor. So there are 3 components to this module. So 40% will be an exam at the end, and that's an RDS. That's a 2-hour exam, and I'll give you examples of that, and we'll talk about that one in advance so you know how to prepare for that. And there should be the last year's exam up on the UCD system. So it's typically like 15 to 20 short questions where you can answer with bullet points. There will be an assignment at week 9. So that will be, you have to set up some model and then write a short report describing different parts of the model, where I give you kind of targeted questions. So I'll put that up in the coming weeks. So I think I will make that available from week 6 or something. So then you'll have 3 weeks to do it, something like that. And then you get, so that's 40%, and then you get 20% of the module just by doing the weekly labs. So in your timetable, you will have a weekly lab for every Thursday for 12 weeks. But there are 2 gap weeks that are not in your timetable. So I'm telling you about them. So in your timetable, it will say that week 4 is a lab, but there is no lab. There's a break that week. And the same for week 8. So week 4 and week 8 are gaps. So I'll put announcements on Brightspace the week before just to remind you. The way the labs work, so you get 20% for those. You don't get a grade for turning up at the lab like this. If you go to Brightspace and you go assessment, assignments, hold on, I think I can look at this from a student's perspective. So if you go assessments, assignments, then basically the lab assignments, each one is a couple of percent, I guess, or whatever it is. So for week 1, for this Thursday, there essentially are 2 video recordings. This is me setting up a model. You just have to follow along and show you were able to follow that, or you submit a screenshot at the end, and then you submit that. And you have 1 week from the lab to submit that. So this is up now already, and actually the first 3 weeks are up. So you can actually just do them now if you want, or like whenever you want. You can do it in your own time. So the purpose of the Thursday lab is that you can be guaranteed that I or teaching assistants will be there to support you if you have problems with it. Whereas outside of that time, if you email, I'll be less available, or teaching assistants will be less available. So the Thursday lab is to support you to do these labs, but you can do the labs in advance if you want as well. So there are 3 weeks of Abacus tutorials. So you'll see there's video tutorials, and then there's also PDF slides to follow along with. And then it just says, do this, submit 2 screenshots here, and you're done. If you submit it and you made a mistake, just submit it again. You'll see as well, just before you do the labs, there's a checklist here somewhere. Student integrity. So I just want you to read it and just tell me that you're not cheating and getting your friends to do your assignments. Okay. So you'll see the first 3 assignments are up. And I will put up the rest of them in the coming weeks. So you can just do them all in advance if you want. And yeah, there's 1 week to do each of those. Then you will also see there's a quiz, an ungraded quiz, which you don't have to do, but if you want, I designed it to help you prepare for your final exam. So the final exam uses very similar content to this quiz. So you can just do it. You can do it as many times as you want. That grade's not use friendly, so you'll get a grade at the end of it. But I don't use that grade for anything. So it's just for practice. So when you ask me what's on the final exam, I could say, well, this is indicative. You can see last year's paper, and I'll give you some hints throughout the course as well. The purpose of the exam is mostly just to check that you learn some of the theoretical content of the module. Any questions on that? Yeah. And on under discussions on Brightspace, I've set up a discussion forum where you can ask questions anonymously. So you can ask questions just about anything anonymously. It can be about the exam, the module, it can be technical questions. And you'll see here that I've, these should be links. Okay, I think I need to change some permissions. I just copied all the questions from last year as well. So sometimes some things that are unclear to students last year will also be unclear to students this year. So you might find that somebody has answered a question you're going to ask. So I will make that available, but you can ask any questions there. Or if you just want to give feedback, I will do a feedback session. But if you want to just give feedback and say, this is a bit unclear, can you provide more details of this, or would be better if you did this, that's fine as well. And let me see anything else here. Yeah, my learning, I'll put up the lecture notes here. So in learning content, so the slides that I'm going through now are here already, and I will put up the slides in advance of the lectures. So you don't have to go through them. It's just some students find it easier to go through them in advance. That's fine. I'm not expecting people to go through them. Sometimes it ruins the surprise of the lecture, but it's for some people who will find it easier for their learning if they want to go through it in advance. The grade scale, so I'm using these alternative grade scale, which on the face of it seems way more difficult. So you have to get over 85 to get an A. But I can assure you that I've designed the assessment with this in mind. So, for example, anybody who just did all the labs last year got full marks for that 20%. The assignments as well, people generally do like very well. So, but I do need to point this out that this is the grade scale used. And just comment on late submission. This is the standard UCD policy. So, for example, if you miss a weekly lab, by 1 week it drops by one subgrade. So A minus to A, 2 weeks it drops by 2 subgrades, and after 2 weeks, then I just don't grade it and I give you a 0. But of course, there are many exceptions to do with extenuating circumstances. If you have some personal circumstances, just let me know and I can direct you how to apply for that. And a common extenuating circumstance is just to move the deadlines for assignments to the end of the year or something like that, for example. Module structured. So we have weekly lectures and we have weekly labs. So there's 2 lab sessions. Think in your timetable, it will say multiple rooms. It might say room 301, 308 or something. So if you go to 301, so that's the corridor above us, the 3rd corridor, and right at the very end. So you may remember that there's a computer room there, but over the summer, well, up until last week, they renovated that space. So now when you go in, there's offices to the right, and then there's 2 computer rooms to the left. And by computer rooms, I say that we're just ordering the computers now, so there's no computers there at the moment. So they're 2 big computer rooms. But they hopefully will arrive in the next couple of weeks. So there'll be 20 new machines there. So I think the labs are scheduled between 3 and 4 and half 4 and 6. That's just to feed everyone. So for the first week, I'll ask people to adhere to the times that you signed up to. But after the first week, I'll see sometimes a lot of people don't go to the labs, they just do it online and they only come when they have problems. If that's the case, then people can just come anytime within that slot for future weeks. But for the first week, just come at your actual time. Yeah, so first 3 weeks, we're going to use Abacus, finite element, then the next, so solid stress analysis or thermal stress analysis. Then we're going to do 3 weeks of computational fluid dynamics with Fluent. And then weeks 9 to 11, we're going to use this OpenFOAM, learn about Linux and this open source software. And then at week 12, it's going to be high performance computing. So it's how to use a supercomputer. So for this Thursday, if you want to make best use of your time, try to install the software before you go. So the module is designed around you using your own laptop. People will probably have questions around problems with their laptop. That's fine. I can help you resolve that there or after this lecture, or you can send an email or do it on the forum. But try install Abacus before. So if you go onto Brightspace, under the learning content, you'll have installing software, and they put all information about how to install software there. But of course, if you turn up on Thursday and you haven't installed it, I will help you, or one of the TAs will help you. Okay. Okay, that's me done. So see you on Wednesday.